In this video, we want to take a look at a geometric approach to the dot product. Now, the dot product is going to be a way of taking two vectors, combining them together, and getting a number as a result. Please keep this in mind as we work with this. The result is not another vector. It is a number. It's going to we call it a product, the dot product, because it's going to act like it's going to have properties that are like a product, distributive property, things like that. However, it does not produce another vector. It produces a number. Okay. So here we go. The definition. Given two vectors, u and v, we define the dot product as u dot v equals the length of u times the length of v times the cosine of the angle. Now, a couple things I should point out here. One is the notation. There is a dot in between the two. With numbers, we have several ways that we denote multiplication, right? We have an x. Sometimes we use a dot. Sometimes we just put the things right next to each other, right? If you said 3x, that would mean 3 times x. Now, we've already used juxtaposition in this course because we used scalar multiplication to look like that. If I have the vector u and I say 3u, it means I'm multiplying the vector u by the scalar 3, right? Making it 3 times as long. Now I'm defining the dot product, which is another way of multiplying vectors together, but it's different than scalar multiplication, and I'm using the notation of the dot. Later on, I believe next week, we will do the cross product where we will have u with a little x next to it and then v. So it looks like I'm multiplying using using an x in between. Anyway, some things to notice here, some other things to notice, is that the book only gives this definition in R2 and R3 because they don't believe in geometry in higher dimensions, I guess. The notion of what's the angle in between the vectors, right? If this is the vector u and this is the vector v, then the angle in between the vectors is this, this angle right here. It's defined to be the smallest angle made by those two vectors, because you could talk about the angle on the outside here, but that would be bigger than pi. So the angle between them is going to be an angle somewhere between 0 and pi. Now, you might think positive or negative because it might make a difference whether I go in that direction to measure the angle or this direction to measure the angle. But from the point of view of the dot product here, it's not going to matter because I'm going to take the cosine of that angle. If you think about the graph of the cosine curve, right, it's symmetric about the y-axis. So whether I take the angle here and take the cosine or take the negative angle and then take the cosine, I'm going to get the same result. So I don't care which direction you do that. So this is maybe only in R2 and R3. Okay. I have no problem with it being in any dimension because it doesn't. You have norms, you have the length, you have angle in between it, just like, I drew these two vectors in R2 and you can clearly see what the angle is, but I could take this picture and, tip it up into the third dimension and the angles would still be at the same angle. I could tip it out into the fourth dimension and the picture wouldn't change. You can still put a protractor between the two vectors and measure the angle in between them, whether you're in R2, R3, or R17. It doesn't really matter. Whatever. Length of one, length of the other, times the cosine of the angle in between them. That's what we call the dot product. Here's an example. I drew this angle, this vector here with length 6, and this vector here with length 4. And the angle in between it, I made it so that it was pi over 6. I actually did plot this reasonably carefully, and this angle is pi over 6 right here. And so the dot product of these two vectors would be the length of one times the length of the other times the cosine of the angle, right? The length of the first one is 6, the length of the second one is 4, and the angle between them is pi over 6. cosine of pi over 6 is radical 3 over 2. And so I've got 24 times radical 3 over 2, and which would be 12 radical 3. Right? I get a number as a result. I had two vectors put in, and I get a number as a result. What does this have to do with anything? Well, we'll see that over the next couple of videos. So, three things I want to notice here. The dot product produces a number, which we've already mentioned, and the direction of the angle doesn't matter. And more so, the order doesn't matter. Because if I said length of, v dotted with u, then this should be the length of v, that should be the length of u. Well, 4 times 6 is the same as 6 times 4, and it's still the same angle in between them. So the dot product here is what we call commutative, that u dotted with v is the same as v dotted with u. Right? There is a commutative property for this definition of the dot product. Now I have a theorem. What's my theorem? My theorem is that the length of a vector is the square root of the dot product of the vector with itself. Well, proof is reasonably easy here, because the square root of the dot product is the square root of the length of the first vector times the length of the second vector times the cosine of the angle in between them. Well, if my two vectors are the same vector, u and u, what's the angle in between those two vectors? Well, it's 0. And the cosine of 0 is 1. So length of u times the length of u is just the length of u squared, and I'm taking the square root of that, and I get the length of u. Now you might wonder, hey, shouldn't I have the absolute value of the length of u? But the length of u is a positive number, so square it and square root it, you do get back to exactly the same thing. I don't need to say absolute value. Okay. Now, one of the things that this definition gives us the possibility of is that it's potentially being able to calculate angles between vectors, because the angle here is involved in the definition. The dot product of u and v is the length of u times the length of v times the cosine of the angle. So I could solve for the cosine of the angle and then, I suppose, take the inverse cosine of both sides. But in order to use this, right, this is the dot product divided by the lengths. I would have to somehow know how to calculate the dot product other than knowing the lengths and the angle in between them. Okay. And this is why we're going to need an algebraic approach to doing the dot product. And that's going to allow us to calculate this numerator independent of the lengths and the angle. So that's the topic for the next video.